Come on, we'll do the academic thing. It is my delight to introduce my. No, Ben's great, and we all know Ben. We all love Ben. So Ben.
All right, thank you. So if I can continue to burp, it's because this carbonated beverage. I'm sorry, just to preface everything. All right, so I love plays on words. So the tier here, I'm meaning compilation tier or execution tier. That's why it fits in this nice little play on words. I hope everybody got that. All right, so this is mostly a one-trick pony talk. So I'm going to talk about, like, well, more than one trick, but it's majority one trick on how to make an interpreter for WebAssembly. All right, so let me give you a bit of background on WebAssembly. So we initially designed WebAssembly for static compilation, and that was all driven by our requirements, the kinds of technology that we were trying to replace on the web. And I remember in the back room, I'm almost certain that I uttered this word for word. Interpreter performance doesn't matter, we're not designing for that. And of course, history makes me eat my words. So I should learn to stop making such ridiculous statements.
Oh, hey, stop. A whole bunch of people just shut up.
Oh, okay. Get some more ropes ready here.
Oh, shit.
Okay, eat bananas. All right, so our assumption was that upfront compilation was worth it. So the kinds of technology that were competitors in the web were like native client and Wasm.js. Both of them had a pretty big startup cost where essentially all of your code was compiled before you started running the application. As opposed to JavaScript, which is going to dynamically optimize things, so you might have compilation costs spread throughout your application, and you would start to see what we call jank, which is basically interruptions in your program as it runs. We wanted to avoid that. So games, they hate jank. They hate it when you miss frames because the JIT compiler is running and you're waiting for code. So we wanted to avoid that. Everything was going to be compiled statically up front, and all the design considerations for the format and the semantics were all about what does the eventual top tier code quality look like. Nevertheless, we weren't stupid. Like, we realized that we're going to eventually need to improve startup performance, so we thought about single pass compilation so that we would get better startup. So you can run through the code in one pass, you can do type checking, you can also generate machine code very quickly in one pass. But really, we were more concerned about what is the final code quality that comes out. So when everything got shipped in the early 2017 and all the web browsers came out, so in Chrome, we only had one execution tier, Turbofan, which is the optimizing compiler. It only had one single thread for technical reasons. It was hard to do parallel compilation in V8 at that time. So basically, you get a module, spend an entire thread burning through the optimizing compiler, compile everything in the module. So if the module is big, you spend quite a lot of time. In Firefox, they have many different monkeys, which they've named the generations. The generation for Wasm was called Odin Monkey. And they did pretty much the same thing. I'm not sure if they were multi-threaded at the beginning, but they did compile everything to start up. JSC was also the same story. I'm not sure if they were multi-threaded either. Shocker was the only, so that's the now defunct Microsoft implementation of JavaScript. They had an interpreter, and I thought they were nuts. But they were the only engine that had anything besides a top tier only JIT. And I think maybe in retrospect, maybe they had a bit more foresight than we did. But the reality check here was that you just release this wonderful thing. It's called WebAssembly. Here you can use it. Go try it out. And like the first demo is like an 8-second pause where your browser doesn't do anything. It's super embarrassing. And so native client, which was a technology from Google as well, did not have such a pause. And so it looked terrible. So it was not great. Not a great user experience. So, of course, you can just throw more threads at it, and that's the first thing that you try. So on desktop, at that time, 2017, you're starting to see like 8 core processors. You could throw 8 threads at it, and you get like a factor of 6 reduction in compilation time. So instead of like 8 second startup, you have like 1.5 second startup, which is great, but it's also 1.5 seconds. It's very visible to a user. And the other thing is that you're never going to have enough cores to make this like kind of silly, complete upfront compilation make sense, especially in mobile. So we were seeing like 10x worse performance on mobile because compilation just wasn't as fast on mobile. It was much slower. They don't have the memory bandwidth, and they don't have the energy to run as big of cores. And of course, you get the sublinear speed up, which is what I mentioned. You don't get that factor of speed up as the number of cores that you have. So it was always part of the plan that we would ship baseline compilers. And that is basically a compiler that just goes a single pass over your bytecode, generates machine code essentially for every bytecode as it sees it. You can do register allocation along the way, but it's like a gajillion times faster. So you don't build an IR, so you don't have like a graph, you don't have an AST, you don't have any of that. It's just like machine code comes out. And the whole point is to be fast compiled. And it really is a lot faster, 10, sometimes 50 times faster generating code than a baseline compiler. But the issue is that you get more code out, so like you waste memory, and also it doesn't run as fast because you didn't do as many optimizations that you would. And so you haven't seen any of the scope of the function, you just really saw one bytecode at a time. So fast forward a little bit to today, actually all of the browser engines are doing this. They have at least 2 execution tiers for WebAssembly. There's a baseline compiler and an optimizing compiler at the minimum, and some of them actually have interpreters as well. Whereas engines off the web, so things like Wasm Time, they might be compile only. They don't have interpreters. They might compile offline and want to do generate like a static binary that you can load. But they're really, that's pretty much where it lies. Okay, so we're in a nice community of people that like this wonderful language called Racket, and it runs on an interpreter. So you probably all know why interpreters are great. You probably write interpreters on top of Racket. So chalk up compilers a lot, but there's a lot of advantages to interpretation. So even though we focused on the JIT compilation for maximum performance, actually there was a plan to use an interpreter, at least in V8, for debugging. So the idea was that, if you stop your Wasm code, and of course it's a bytecode, so maybe you want to use some source level information, but eventually it boils down to stopping the bytecode somewhere and stepping through the bytecode and seeing the state of the virtual machine. And our plan was to use a C++ interpreter for that. That never really happened. It ends up now that actually V8, if you debug WebAssembly code, it happens in the baseline compiled code. But I did write the C++ interpreter. It was very slow. It was like 1,000 times the compiled machine code. And so for that reason, it was a little bit,
1,000 times slower than the baseline compiler?
No optimized compiler.
How did it relate to the baseline compiler?
So the baseline compiler, you'll see benchmarks later of where where baseline versus opt comes down, but it's typically 2 to 3 times slower than optimized code. So, of course, but we're facing these issues. Cold code, meaning code that is either executed once or never executed at all. There's absolutely no point in compiling that. You do not get any speed up from using the compiler at all. And of course, that takes memory. If you're compiling all that code that doesn't run very long, you don't want to do that. And of course, all that takes time. So all these are really good reasons just for performance to use an interpreter. So why spend time compiling code that you're never going to run or rarely ever run? Same thing with space. That's often overlooked. It's one thing that we often end up tuning in web engines is that web pages have a lot of junk in them, and you don't want to spend a lot of memory on that junk. So even though we constantly focus on, is an interpreter faster or is a compiler faster? It takes memory, and the interpreters are all about saving memory. So there's a side effect of using an interpreter. It's simpler. Well, unless you write an assembly language, which I did, it is simpler. And so you can trust it. So there's no dynamic code generation going on in an interpreter. You can theoretically verify the machine code that's there, and as long as the data structure can feed into it, it's a lot safer. So it's easy to see that an interpreter is correct. And so if you see the mechanized, formally proven implementations of WebAssembly, they're all interpreters that are proven correct against the formal semantics of WebAssembly. So you can trust an interpreter more. The other thing, it turns out that people want to do more than just run code. They want to look at code. They want to debug code. They want to do dynamic analysis on code. An interpreter is great for that because it implements the abstract machine directly, so you can stop. You can look at what the state of the machine is. You can step it. So that's a really nice property of an interpreter too. So it turns out Wasm is not easy to interpret. So that thing that I said about, nobody cares about interpreters, we intentionally dumped on them. So there are constructs in WebAssembly that are difficult to interpret. In particular, one of the more controversial things that we decided to do, which is you can kind of think it as almost as a space optimization, is that there's structure and control flow in WebAssembly. So there aren't jumps, there aren't branches, there aren't jump tables, there are blocks, and there are loops, and there are ifs. That means that you can only express reducible control flow, but it also means that the validation algorithm is faster. So I don't have time to go in all the details of why that happens, but we did that for a really good reason. Compilers don't care that it's structured control flow. It actually improves their ability to either generate their IR or generate their code faster. But interpreter hates this because you don't know where to go. So you have an if, you have a block, you have a loop, and you have a branch, and it's like, where are you going? And it's all the relative nesting depth of the construct that you're in. So the immediate that's in the code, it doesn't tell you actually where to go. So an interpreter that's looking at the bytecodes one by one, it doesn't know where to go. So there are interpreters now. So I mentioned all the compilers that came out in the beginning, but actually now JavaScript Core, which is in Safari, Shocker I mentioned before, but there are several other implementations of WebAssembly that do have interpreters. And every single one of them translates the bytecode. They translate WebAssembly to a new form internally that they then interpret. And it's partly because of the control flow constructs. It's partly because they maybe want to run the code faster, but they don't want to generate machine code. So both Wasm 3 and I think there's another one, WAMR, which is not on the slide, they translate because they want their interpreters to go really fast. So they do some optimizations to make their internal representation faster to interpret. But it also at least doubles the memory consumption of your code, because now you've got another representation of it. So even though you're not generating machine code, you're generating something, and that something takes memory, and so you're blowing up the memory space.
Why? It only doubles if you keep the original around, right?
Because if you're going to debug, then you need to keep the original code. So,
question.
Yeah, go ahead.
I might be stupid. I don't understand why the structured control flow is so hard to interpret. I feel like you're going to have a register that's going to say, this is the place where if you branch to. Or this is like what the join point is. It's basically like you have a little stack in the interpreter that tells you where the structured control is.
So if you do a dynamic control stack, which is what you're talking about, like you basically push, like this is the block I'm in, you don't know where that block ends until you scan forward, because it's like, if the block told you I'm going to end in the future, then you could do that.
I understand what you're saying. So basically there's just this stream of bytecode, and you have to get to the end to know that you're in with the block. There's basically like a bytecode that says, block is over.
Yep.
Okay, now I get it.
Yep, there's an end bytecode. So the other thing is that control flow is not just blocks and loops and ifs, but eventually there's going to be exception handling, and those things are not going to be obvious how to interpret those things. So it's going to get worse in the future. We actually don't have let in the function references proposal anymore, but that would have been an issue too. The other thing is that, some other bytecodes are actually kind of a pain in the neck to interpret too. So that where all this kind of leads to is that maybe you don't want to interpret the original bytes. It starts to sound like a bad idea. And basically everything else that you can think of, like there's some space overhead. Like maybe you could pre-process the bytecode and have some side information. That's actually the solution I'm going to have, but until this paper, which is coming out in Newsletter, you can actually already read it, there wasn't a way to do this that was actually designed for an interpretation. All right, so to recap, we rewrite to a new format, we're wasting time and space. It's almost as complex as compiling. You have to track all the abstract state that you would have to track in a compiler. It's maybe just a tad simpler because you don't have to do register allocation or generate assembly code and then debug that. So it's a little bit easier, but it's basically fundamentally the same algorithm as compiling. So with my one-trick pony here, we're going to directly interpret the Wasm bytes. So the way it worked out in the interpreter that I mentioned before in V8, the C++ one, there was a side table, but it was not set up to be indexed in constant time. So there's always a search. There's a login search because it was sorted. So I fixed that. Now it's 01, and I'm going to go through exactly how that works. So I also am insane, so I wrote an assembly language I actually thought that was really fun, but I wanted to see what the ultimate sort of performance limit was, kind of a limit study. The reason why I did that also is that simply the standard bytecode, it doesn't change very much. So once you implement it, it's pretty much going to stay there. So it's not something that you constantly refactor. So I think this is like the software equivalent of burning it into hardware is writing an assembly, and I feel justified that it's okay. I'll probably eat my words there too. So the benefit is obviously no rewrite step. There's also some neat tricks that I can do so to get a faster calling convention. So calls are actually faster than they would be in the rewriting interpreter. And I meant to update this slide. It's not 10% space overhead. That's a lie. It's like 30% overhead. But that's pretty good.
Shame.
So that's, go ahead.
I said shame.
Shame, yeah. Well, that's versus 2 to 5 eggs for a JIT to machine code. That's about what you pay. And I have some numbers for this with students and graphs. All right, so let's get to it. Let's think about how this interpreter works. Pretty much every interpreter has things which are basically the state of the interpreter. You can think of them as being registers, and in fact, they will ultimately become registers. So when you write an assembly language, like every one of these is going to get its own register. But the state that you need to interpret WebAssembly is you have to know where you are in the code. That's IP, that's the instruction pointer. So that points directly into the bytes that you got off the network that are in memory. Nothing's been changed. You point right in there. So right now, like you can just imagine that we're at the call instruction. So there's a pointer directly to that byte. The other thing is that WebAssembly allows you to fall off the end of the code, and that's legal, and that's an implicit return. And every time you execute an end instruction, you basically have to do that check. So I found that it was faster to always keep a pointer to the end of the code, so you could just check if I've fallen off the end of the code. You can get to the end of the code, for example, by going through the function and then reading the code pointer of that and then reading its length. So you could have it's not fundamentally required to have a pointer to the end of the code, it just happens to save you a couple instructions. So then there's the other thing. It should be actually STP, but that's going to be the side table pointer. So the side table is going to be this additional piece of data here in the middle that's going to make all these troublesome cases of these branches easier to do. So if you look, the side table is actually sorted so the entries line up with where they are needed in the original code. So this is like the entry for the first one. So every one of them corresponds to a branch. So an if is a branch, an else is actually a branch, which is a jump to the end. And then there's a BR if here, which is another conditional branch. So those are going to be side table entries for each of them. So the other thing about making a fast interpreter is that you need to have a representation of the abstract state, like the state of the machine. It's not even the abstract state, it's the concrete state of the machine. So that's the value stack. So in WebAssembly, it's a stack machine, so all values go onto the stack, all operations happen on the stack. Oh man, come on. Maybe you have to go over here. All right, so basically WebAssembly has, I think, 6 different kinds of values, and they fall into the categories I32, which is a 32-bit integer, I64, which is a 64-bit integer, F32, F64, which are floating point numbers. Can we get it? Okay. And also references. So distinguishing what kind of value you have isn't really necessary for executing WebAssembly because it's not dynamically typed. You never have to actually look at the type of a value to do something. That's statically in the bytecode. But a typical VM does actually want to find where pointers are, so references to, which in this case, which would be external objects. So having a value tag that tells you that this is actually distinguished from, for example, an F64 is necessary unless you want to do conservative garbage collection. So the value stack in the wizard interpreter actually does dynamically track the value tags. So you basically need to have a pointer to the quote unquote frame pointer, which is like where this function's local variables start, and then the stack pointer moves up and down as you push operands onto the stack. So then there are other things that you can do in WebAssembly. For example, you can call functions and you can load global variables, so all that state hangs off the instance. There's a couple of things that you might need from the function, and of course you need to get to the WebAssembly memory often, so there's a register for that too. Are there any questions about that? Yeah.
What do these numbers on the side table mean?
We're going to explain that. Am I going to explain that? I hope I'm going to explain that. Probably the time to explain that now. Okay, so the issue is that when we get to an if or an else or a BR if, we don't know where to go in the bytecode. So we're stepping through the bytecode, we don't know where to go. Do you have a question too?
Yeah, so where are the locals on the stack, or are they in extra?
They are in, so the value stack stores both the locals and the operating stack. Okay, so we don't know where to go when we have a branch. So the side table entry is this delta IP. So if we get to this if, and we decide that the condition is true, we're actually going to follow through. If it's false, we're going to jump to after the else, because that's how if works. So what this delta IP is for that entry is where to go if you are going to jump.
So the 7 is to the else.
Yep.
But what's
no,
the 8?
It's to the end. Sorry, yes, you're right. It's to the else. Now, the XIP. Let me skip that for a moment. These two will also make sense. We'll come back to the XIP. It's called STP in the paper if you read it. So the other thing about WebAssembly is that there's an operand stack, right? So we're pushing values here, and we're popping them off. If you exit a block in WebAssembly, it can also implicitly pop some values off the stack. So you can be very deep in a block, and there can be many operands on the stack, and then you can break to an outer block, and that's supposed to pop values off the stack implicitly when you do a BR. So that's basically these two numbers. It tells you how many values to pop off the stack and how far. So whenever you execute a branch, whether that be a BR if or an else, you use these two numbers to tell you how much to adjust the operating stack. Does that make sense? Questions about that? Okay. And then the last thing, the XIP, which I should have renamed in this slide, but I keep forgetting. That is actually the adjustment to this pointer into the side table. So the trick is that the side table pointer, or the XIP, always points at the entry that you're going to need next. What is wrong with this issue?
You can turn your battery saver.
My battery saver?
Yeah.
Get the caffeine app.
Full power.
Do you have to touch something
It'll
again?
be fine. It'll just come back.
It's just slow? All right, so the issue is that basically the XIP always points to the side table entry that you're going to use next. So when you start off in the beginning of the function, it always points at the first entry. And so when you hit the first branch, it already points at the information that you would need to know that you're going to use, whether you take the branch or not. And the issue is that if you do take a branch, it means you're not going to the next bytecode, right? It means you're going somewhere else in the code. So you're definitely adjusting the IP. If you also adjust the STP, then you're going to point to the entry that's going to be needed for that.
So this prevents searching.
Yes, so this is no searching. And since you know statically where you're going, you also can match that up with the side table entry that you need to go there. So this is the one neat trick that makes interpreters go fast. Yeah.
I don't fully understand the doesn't need searching. I thought the whole point was we already knew that
The delta IP is not enough. You need to know how, because think of it this way, like there could be a bunch of side table entries inside of here, like the true block that you need to.
The nested, this is basically because of the nested.
Yeah, and also imagine like you go back in a loop, so you need to know what the next entry is. But you always do, it's static because it's just the control flow. So there's no searching. The other thing is
and
that
then the entry for the else is for the join.
yeah, so when you hit an else bytecode, you know you're done with the true block and you jump over to the end. Yeah.
So if we hit the if and we don't branch, do we also update the XIP pointer?
Yes, we do. We have to skip that entry and go to the next one. So the key thing here is that these are also sorted with respect to the bytecode. Because that's how, like, you kind of start off with the first one. If you don't take the branch, you go to the next one, right? You just keep falling down. It's only when you do branch that you need to move in the side table pointer, in the side table. And the awesome thing is that generating the side table doesn't require any sorting either.
Point with your mouse both so we can see it, and that way you'll be jiggling your mouse periodically.
Oh, very smart. Yes. So,
Step away from the board, sir. You can't see where you're pointing from back here.
You know, Shriram, you could come up and occasionally move the mouse.
yeah, you can move the mouse. So the entries come out of the validator in order because the validator runs through the code in order. So as you see a bytecode, you know you need a new entry. And so it basically just poops out the side table as you're going along. So there's no sorting steps anywhere. So it turns out that that's actually like, if you take the amount of time it takes to validate the bytecode, it's something like 20% of that. If you add 20% of that, that's what it takes to generate the side table. And again, it's like you can see that it's small, right? This thing typically ends up being about 30% of the original bytecode. All right, now we got a bunch of choices. We got the idea, we need to implement it. So we've got to choose an engine, we got to choose an implementation language, the dispatch mechanism, which is the thing that actually executes the next bytecode in the interpreter, choose a value stack representation, figure out how we're going to make the execution stack of Wasm frames look, and also what we're going to do about the host language garbage collector. So these are my initial design choices. So I have this research engine, which is Wizard, which is the thing that I implemented all this stuff in. That was basically non-negotiable because I'm not going back to writing C++ in V8 because for my own sanity. So Wizard is written in Virgil, which is a language that I like, which is a language actually I designed long ago and still work on. But the dispatch mechanism, which is basically how are you going to execute the next bytecode, I was like loop over switch, obviously did, right? And then value stack, which is like how you're going to represent values. The easiest thing to do is you write it using the language mechanisms that are easy. So in this case, Virgil has algebraic data types. So you just write a nice algebraic data type which represents your values. Unfortunately, that will be boxed. We'll see how much that sucks. And then the execution stack, basically the interpreter just keeps a list of frames. And like you said, it's just literally a stack of frames. You just keep pushing and popping. And then because the value stack representation is boxed, it basically means that you're using the host language TC.
Wait, what do the colors mean on this slide? Is red bad, or is red something?
Red is going to be slow. Although it's not really because of Virgil that it's slow, but
Yeah. Of course not.
it's mostly this. It's mostly this.
And that box is like in contrast to the sexy man boxing that we always hear about, right?
Yeah. So if you do that, it runs slow. So it turns out that like all of this, so this is the Polybench benchmark suite. This is all the line items. The baseline here is actually JavaScript Core's interpreter. So one, which would be like down here, is like running in an interpreter already. So it's not fast. And it's all because of the boxes. So that was like stupid. Like not. So if you're a grad student and you implement something and you get numbers like this, do not be disheartened. Just rewrite it in assembly. It'll be fast.
Sorry, what should we have known what Wasm's 3264?
Oh yeah. So this is compiled to 32-bit x86 Linux. This is actually probably before I had a new register allocated. But you can see these are 3 different targets for Virgil. So 32-bit x86 Linux, 64-bit x86 Linux, and then running on the JVM. So actually, you can run WebAssembly on the JVM by compiling Wizard to the JVM and just running it like basically vanilla. And it turns out the JVM hates Virgil code because I do a lot of first-class functions, and I do the whole thing that like everybody does that sucks. So, despite the tons of optimizations gone into JVMs, it really still sucks for kind of functional code.
Question.
Yeah.
This is probably unrelated to the talk, but why is the 64 like always so much worse than 32?
Register allocator. They're completely different backends, and I did not do a good job. I have a better register allocator, so those numbers are
So they're not
closer.
quite comparable.
No, but you can see how much the code quality of the Virgil compiler impacts the interpreter. Okay, but there's this one there that's not so bad.
Oh yeah, only 5 minutes.
All right, so we're going to change all the...
Scale.
Yeah, not a log scale. Yeah. Great idea. Out of line with statistics, right? Okay, so change the design questions. Because I was like, that whole experiment basically said, oh man, if Virtual was really fast and it generated the absolute best code that I can think of, it would be great. Like that would give us the best signal. So I'm like, well, maybe we'll just skip that step and I'll just write the best code that I can think of. So that was x86 64A. The other thing is that it turns out that like just having a loop over a switch, there's some tricks that you can do to make that even better. So that's the threaded dispatch mechanism. So try that. But also it's like quite obvious that you spend all the time allocating these objects to box the values. You don't want to do that. So I experimented with a couple of different things here to make that way more green. As green is good. And also, instead of just like having like a data structure, which is a list of your execution frames, just using the host execution stack, meaning you need to have custom frames, that also you can do some tricks there. So basically this is more of a limit study, like how far you can actually go. The other thing is that value representation and that value stack is going to require some tricks to integrate the host GC. Because I'm basically putting virtual pointers into a data structure because I'm writing it all in x86 assembly that the host, therefore the virtual garbage collector doesn't know. So you need to actually tell it about it. So there's like a little plug-in in the runtime where you can add a scanner to tell it about some pointers that it otherwise wouldn't know. All right, so that basically boils down to the same picture before, but like adding registers. So we can actually, thankfully they finally got enough registers on x86 that you can put them all in there. So there's 16, so there's a few left over. I actually was careful in choosing which ones went where, because the ones that actually, so the lower 8 actually save you a byte in the encoding. So if those show up a lot in your interpreter code, you want to use those more often. So like RAX and like RBX, RCX, all the classic ones, I use those for the really common occurring things, and the things that you don't use very much, like I don't think you use the function very much, like that's in R12. And also the frame pointer, I think that one doesn't show up that much, because it's only get local and set local that are that one. So there's that. The other thing is that obviously if you write in a high level language, somewhere there's like a byte array, which is the code. So you do bounds checks if you go through like an interpreter loop. So if you're writing an assembly language, like you have verified that this code has gone through the loader, you cannot possibly go out of bounds. So you don't need bounds checks there. Similarly here, for the same reasoning holds, like you can never really prove this to the host language that you're in bounds, because the property that you're proving is a property of the data structure of the Wasm code that you verified in the Wasm type system. That's like basically impossible with today's technology to prove that's in bounds, so you just have to cheat. So just cheat. The other thing is actually this one is really tricky. So we go back to the value representation. So if you look at the paper, you will see exactly what it looks like. But basically these values on the value stack, they are 32 bytes wide. And the reason for that is that you need to have, first of all, you need to have a byte for the tag, the value tag. But the values can be as big as 16 bytes because Wasm has SIMD now. It has 128-bit vectors. So you can actually have values that are already 16 bytes, and you need at least one more byte for the value tag, and then you round up to a power of 2, that's 32. So every one of these things on the value stack, there's a flag that you can swap it to not support SIMD, but every one of these values is 32 bytes. And it's kind of fine because you mostly just don't touch those bytes that are over there, and so I didn't really see such much of a slowdown. But that means that you're not boxing anything, not allocating anything on the heap. So when we do an execution, we're just like writing a value tag and then manipulating the bits here. And actually often, like if you do like an I32 add, actually the tags don't change, so the interpreter doesn't actually write any value tags. It's really only when you when you introduce a value where the tag was different than before. You actually need to update the value tag on the stack. Does that make sense? Questions about that?
It feels really scandalous. 32 bytes every time.
That was ultra fast for me. You said you don't allocate anything on the heap, which obviously that's not.
The stack is allocated once, but then as you're executing every bytecode, like none of the bytecodes need to box anything. They're just writing into various points in the value stack and the locals as well.
If the, as you mentioned, the sort of the only type you really care about treating differently is reference, although maybe you don't, why not just have ref be the tag and let the other ones just sort of be ref or no ref?
That's an excellent question. It's because the interpreter has to decode the Wasm locals, which are encoded as like bytes. So like at the beginning of a function, it's like, I want 3 I32s. And the encoding of that is actually like a Wasm type, and it comes in like various flavors, right? I just load that byte and smash it in as the value tag. So that's actually cheaper than figuring out like, or doing a branch. Is this ref or is this not ref? You can just take the byte that you got and just boom.
That makes sense.
Yeah. It also helps because on the integration on the other side, so if you call code in the runtime, eventually you're going to load these values and you're going to make meta values, right? You're going to make boxed values that the runtime uses. It's nice to have that type tag there because that's the dynamic check.
Okay.
So it will box the thing, and then in the sort of the virtual code, then you're going to get a type error if you screw up. So it's like a nice check when you cross into the virtual world. The other thing is you can't afford to do a bounce check here because like if you did a bounce check on every push and pop to the stack, you're dead. So you just use a guard page. And since it's a value stack, you're always like kind of growing like one at a time. And so you can't like just jump way into the future. So like one guard page is enough. You'll hit the guard page, boom, it's Stack Overflow, game over, and then you generate an exception. So you handle it gracefully, but without any checks, explicit checks in the code. All right, so we have the value stack guard page 2. Same thing for the execution stack. So the execution stack, if you know your x86 in and out, there's RSP, it goes downwards, you're like pushing frames. So I decided to just like use the native execution stack for execution frames of the interpreter. So when you call a function in Wasm, like you get another interpreter frame. So those just keep kind of stacking up. So they can be mixed with virtual frames. And they're basically, like every interpreter frame is essentially just a copy of the registers that you had. You just take the registers you have, you like dump them on the stack, and then you call the thing and it makes its own registers and then it comes back to you, you reload them. So these are all fixed size. None of the values are stored in the execution stack. So like every frame is exactly the same size. So that actually is kind of nice. Questions about that? Oh yeah, so there's another trick here. So this has to do with the numbering of how Wasm locals in the operand stack works. So when you make a call in Wasm, you push all the arguments that are going to go to the function onto the operand stack, and then you call the function. So if that's an indirect call, the function you're calling is like the last value. If it's a direct call, it's an immediate in the bytecode. So those actually become the locals of the callee function. So they actually kind of overlap. So if I like push a bunch of arguments, then if you actually chop up those arguments, those are like the beginning of the next frame. So if you separate the value stack from the execution stack, you can overlap them. So you don't have to copy in the arguments going out. It's a neat trick. Actually, I beat all the other interpreters on call heavy benchmarks just because of this. Genius.
Good job.
Yeah. I don't think so. I think they just explode in your face. They don't handle Stack Overflow gracefully. Yeah, so there's another thing. So the locals actually come first, as I mentioned before. So there's inline assembly in the interpreter when you enter a function that like decodes that stuff. So that's why you had an excellent question about why the value tag, so that dumps the value tags on the value stack. The other thing is I tinkered with this dispatch mechanism with the dispatch table size. So originally I was like, we don't need to make that really small. Let's do 2-byte entries, and then we'll have like an area where the interpreter code is. We'll load 2 bytes and we'll add to that. It turns out that if you're able to put all of your code in the low 4 gigs of memory, then these only have to be 4-byte entries. That's worth 5%. So instead of having 8-byte entries, you have 4-byte entries, 5% execution time for the entire interpreter. So just being able to stick it in the right memory region. So other things that I did is like, there's a lot of LEBs. in the Wasm format, so like I32 cons to like all the local gets, all those things that are immediates in the bytecode, which is like bytecode some stuff, those are almost all LEBs, those are variable length integers. So I like got the inline case of that. I like tuned the crap out of that with the assembly code. You have a question? Okay. The other thing is so loop over switch. So that's the typical thing when you think of writing an interpreter. You have a loop over the bytecode, and then every bytecode goes back to the beginning of the loop. But there's this thing that's been known for at least 45 years, which is called threaded dispatch, which is you just make a copy of the dispatch at the end of every handler. That's worth like 25-30% execution time in the interpreter. So do that every time. Like there's no point in even arguing about that. So you just get a copy of the dispatch sequence. All right, so then when we do that, now we're running again the same baseline. Baseline is 1 now. That's the JavaScript core interpreter. That rewrites the bytecode. So they even have an opportunity to optimize the bytecode. They typically don't very much. So they're mostly running like pretty much the same code, except they rewrite the control flow. So now we're really kind of at par. You can see it's kind of a toss-up. There's things that are a little bit slower, a little bit faster. The 3 things here, these are all, so the baseline is JavaScript core. These are 3 different versions of Wizard. And the untuned one is with none of those tricks, with like the hand-rolled LEB and like the 4-byte dispatch and like other stuff. None of those. So those actually make a difference. And then that is with all those tricks, but still using value tags. So there's a thing where I can switch off value tags to see how much they cost. You have a question?
Yeah, remind me which one of those you were already performing pretty well against.
There was one
They all sucked.
that was.
Oh.
There was one that was only 5x. It was over down here.
It might have been that one. It's in roughly the same area. Yeah. It might have been that one. I'm not sure exactly why that is. So yeah, the green bar still has value tags on, and then the red bar is no value tags, so empty is no tags. And it turns out that like the delta between the green bar and the red bar is like kind of somewhere between 8 and 15%. So the value tags, which are necessary pretty much only for the garbage collector, those cost you about 15% in the interpreter. But if you turn them off because you want to go fast, maybe because you don't have actually any garbage collected references, maybe your external refs are not actually pointers that you need to go find, then you can run a little bit faster. So there's like, you can see many below the bar, there's still some above the bar, but none of them are 10x, none of them are even 2x. So we're really in the same ballpark. Okay, so that was my initial data. This is now data from the paper, which is even more updated. So this shows a lot more execution tiers. So now we're actually going to compare against compilers. Okay, so now the baseline is totally different. It's pretty much the same benchmarks. The order is important here. These are shorter running, and these are longer running. So they're ordered by how long they take to execute. So these ones over here, they take like 100 milliseconds or something like that. At the end is like maybe 2 seconds, so just to get the ballpark. And they're all normalized to themselves, right, as before. But the 1.0 now is V8 turbofan, which is like an optimizing compiler. So the ones over here, like they've had enough time that like the optimizing compiler, like the compilation time doesn't matter that much. So there's like tons of information in this graph. So let me walk you through it. All right, so we've got an optimizing compiler is the baseline. That's 1.0. This is only execution time. The red bars are 2 other optimizing compilers. So JSC is the OMG. I think they have I don't know what it stands for, but OMG is good enough, right? That's their optimizing tier for WebAssembly code. SM is SpiderMonkey, optimizing tier. So if you look at the red bars, I mean, there's some variation here, but they are, like, generally speaking, when you get to longer running benchmarks, all the red bars are the best, they're the lowest, right? And then we've got 3 baseline compilers. Those are the blue bars. So JSC's baseline compiler, SpiderMonkey's baseline compiler, and then V8's baseline compiler. And then the green here is actually an interpreter, but it's not Wizard. It's actually Wasm 3, which is another interpreter that does rewriting. So I did a comparison in the paper about that. Wasm 3 is actually faster than Wizard. We'll see that in a second. But the idea here is that I wanted to see, where do interpreters for WebAssembly actually compare? Like, how do they like fall in the sort of layout of space compared to compilers. You can see actually over here for short running programs, interpreter spanks all the compilers because the compilers like spend all their time compiling and it's not even worth it. I don't know if I have the patience to wait for that again. So like over here, Wasm 3, the interpreter, is the winner. Like, so that's like a stand-in for all the cold code in your program or the startup code in your program where it doesn't even pay off to compile at all. Interpreter wins. Okay, but the baseline compilers also, you can see that they're also faster because there's compile so much faster, but they don't quite win against the interpreter. Then we get into this
Do you know how fast those are? When the green starts to get slower? Do you know how many seconds that is?
This is probably around 250 milliseconds. So then you see that actually there's a couple, like these two right here, where there's actually a blue bar that's best overall. So there's a couple benchmarks right in this middle region where the trade-off between compilation time versus execution time is really starting to transition from like, yeah, you should spend more time compiling. And so there's a couple in there that if you just had a bad benchmark suite or you just changed the numbers just a little bit, it would be like, hey, baseline's the best, right? Whereas if you're over here, you'd be like, hey, interpreters are the best. Whereas if you're over there, it's like, hey, optimizing compilers are the best. This is why like having a broad benchmark suite and like really measuring a lot of different things across a big spectrum is important because you could get the wrong picture. The other thing is you see this obvious trend, right? The interpreter is not getting any faster. Like you're not amortizing anything away. It's just you're finally getting to the raw execution speed. And it kind of levels off here. Like if there were benchmarks beyond, is kind of around 10x. So a lot of people are like, hey, yeah, interpreters are 10x slower than JCompilers. That's true. That pretty much is true. And that's actually a really nice result, so you can just kind of keep that in the back of your head. Like, yeah, interpreters and JCompilers, at least in the case of WebAssembly, yeah, it's almost exactly 10x difference. But again, the amortization. All right. This is interpreters only. So it's going to be a different baseline. Now the baseline is actually the green bar from the last graph. So we're going to normalize all the interpreters to the fastest interpreter that I found, which was Wasm 3. Okay, so what are the different ones here? So there's this thing called Wimmer, which is the WebAssembly micro runtime. This is also another interpreter. They also rewrite the code. They also have taken great pains to make the rewritten thing very easy to interpret, to be fast. So they actually have two variants. Their classic one does actually interpret the bytecodes in place, but they have a search. So they do like a dynamic search to find out where to go. So they don't do the wizard trick. The green bar here is actually wizard, which is what I implemented, and then the yellow thing is JSC interpreter. So it's like kind of like that first graph that I showed you. And so what you see is that there is a 3x difference in interpreter performance across the different ways of doing it. So if you want to do rewriting and you spend a lot of time thinking about what's the best representation, what Wasm 3 is actually threaded code where it's like literally a list of function pointers and you load the function pointer and you just jump to it. That will give you about 3x in interpreter performance. Whereas if you're rewriting but you don't do any of that, that's kind of JSC, that's the yellow bar. So, I'm sorry for these colors, I should come up with something better. But the yellow bar you can kind of see. And if you compare wizard and JSC int, they're often, it's pretty much the graph that I showed you before, like the comparison between those two. Sometimes wizard is a bit faster, sometimes JSC interpreter is a little bit faster, but they're really roughly comparable. And you see there's not really a trend. There's a bit of that same effect of like these really short ones, like the rewriting interpreters are penalized a little bit because they actually have to do the work, but you can't really quite see it here. I think if there was even smaller benchmarks, you would see a bit of a trend of the previous graph, right? Because all those rewriters have to do some work. Questions about that? Oh, no, wait, I just touched it. All right. This is the money shot here, right? So
The black screen?
Yeah, I gotta say,
Yes.
all those graphs, they were not I1.
they're not I1.
All the graphs that you just showed, they were not wizard is the best.
Yeah. That's
This
how
one-
it comes out, you know.
This one, I feel good about this one.
Yeah, well, when it comes up here, I kind of want to wait for it to be on the. Let me get a good burp.
I mean, it does seem to be as good as in most cases as other interpreters, but also better in these.
Right.
How is the extra cost of the validation? The bytecode validation has extra work it's doing in the wizard.
It's in this graph, which is the money shot. All right, so now we see this is a trade-off space, right? So it's not just the execution time. That was just the one dimension that I showed in all those graphs. It's actually the processing time. And so I realized, actually, if I normalize the processing time to how much code you were processing, then you get a comparable thing, right? So this is the processing time per code byte in nanoseconds. All right, so the optimizing compilers land all over there because they spend the most time compiling and they get the best code out. Like this is literally the same data. I did not make this up. So this is all like 1.0. All the optimizing compilers run pretty much right in this little region over here. But the baseline compilers, you can see, like they're slower in terms of their execution time, so they start moving up this way, but they compile code so much faster. So this one is almost 100 times faster than an optimizing compiler. So they're moving this way, right? JSC's baseline compiler is not so baseline. They actually build an IR and stuff. You can see they land there because they're basically building an IR. These two do not. And then you see actually all the rewriting interpreters, they actually spend a lot of time. They spend almost as much time rewriting as a baseline compiler does compiling machine code. But since they don't generate machine code and they generate an IR and they interpret it, they're all over here. So they're like getting that 10x from the interpreter to baseline compiler difference. And so the key is that Wizard, because it's just that little delta on top of the validation time, which is building the side table, it's way over here. So the processing time that you need per code byte is like very, very small, but then you're running, obviously you're running an interpreter, so you're gonna be in the 10x range. So, but it like pretty much lines up with the rewriting interpreters. So like this one, I think is Wasm 3, you can see it's a really fast rewriting interpreter, but like, it's an interpreter, right? And so like JSC int is like, JSC int and Wizard are like kind of the same thing, but shifted over by how much work you have. You've got to be kidding me.
So
This doesn't happen for everyone.
I should probably just plug in my laptop to power.
is this actually the right metric?
There are more metrics, which is on the next slide.
Oh, okay then.
Okay, so Wizard wins here too. Yes. All right, so this is still execution time, so it's going to be the same scale, but this is now space. So this is the space overhead per code byte. So for every input code byte, how many bytes of extra space do you need? Right, so 1 is like you need to generate 1 new byte for every byte that you got in. 0 would be you generate 0 new bytes for every byte that you got in. And you can see actually that it kind of doesn't matter whether you're a rewriting interpreter or a compiler, you have to use a lot of space. So like all the compilers kind of cluster around here. They generate 2.5 bytes for every byte of input code. And this is just machine code. This is not the metadata, like the de-optimization and all the extra lookup. So it's actually being generous. If you added that, they would just further move over here. There is one rewriting interpreter that is almost one-to-one. That was JSC int. And that's because they rewrite to a stack machine. So it's almost like literally they just translate everything is pretty much just the same except for the control flow. So they basically don't blow up the code, they essentially just copy the code. And then of course Wizard is just the side table, right? And the side table is like roughly like 30% of the original code. So it lines up right there. So that's the trade-off, right? So this new part of the space is basically that you see.
What's the bottom left?
The bottom one?
There's a bottom left yellow thing.
There's one yellow
That outlier, I don't know why that happened.
Oh, okay.
That's Whammer, that's Wasm 3. I don't know why that one happened. I gotta look closely.
Okay.
All right, so any questions about that? So that's like these two, I love these graphs. These are in the, like, I tried to put them as early in the paper as I could, because this is a trade-off space, right? So now we're gonna talk about the other things that are great about an interpreter, which is not just its execution time and space characteristics, but you can do things with it, right? Interpretation allows us to do stuff to observe execution and implement instrumentation much easier. So for example, this is the code that we had before. Maybe I'm really interested in doing something every time the program hits this instruction. It's a point of interest in the code. So an interpreter can handle this quite easily. And so I have a neat trick that basically, if you want to insert some functionality and get a callback whenever that instruction executes, what Wizard does is it will just make a copy of the original code, and then we just overwrite that 1 byte with an illegal instruction, and I purposely picked a very ugly color because the ugly color will cause the interpreter to say, illegal bytecode. And then what happens is that you can do user callback. So you can write that in any language that you want. If you write it in Virgil, then you can integrate it directly into the engine. So then you can look at the interpreter state and so on. And then you just redispatch through the original bytecode. So in this way, like you hit the instrumentation, you know exactly where you are in the code. So you don't have to have any translation tables between like any rewritten form would need to have those translation tables. You don't need to have that. You know exactly what bytecode offset you were at.
And you're not constantly checking for a probe.
Exactly. You only hit it when you hit that one spot.
So,
Yeah.
sorry. Does the probe then also have its own entry dispatch table, or is it
It
just a
does.
generic illegal instruction?
It's an illegal instruction, but it's one that's not in the spec, so I can use it internally. Yeah. All right. So the other thing you want to do is maybe sometimes you want to do something simple, like just trace the bytecodes as they come out. Maybe you want to do that inside a particular function, maybe all functions. And so I thought about well, you could add a probe to every single bytecode in the entire program, and then you eventually just hit the probe over and over and over again. It's kind of a pain. So instead, I got this new trick, which is the dispatch table register. So since we've got lots of registers lying around, I only used 9 of them for the interpreter. Just burn another one of them, and that one actually points to the dispatch table that you're using. So normally, R14 is going to point to the normal dispatch table, which is going to go to the interpreter handlers, so the opcode handlers. So when you do dispatch, you load, you add it to that, and then you land an opcode handler. But if you want to get a callback for every bytecode, we just swap the table. We just change this one register. It goes to the instrumented bit dispatch table, where every single one of them calls the probes and then does a dispatch. So by just swapping one register, not changing any machine code or running anything else, boom, now we can do instrumentation. And because of that, we can switch back and forth. So now you can have a probe that's at a location that turns on global probing and then just switches over and goes back. So I implement this to hey, just please trace this one function. You put a probe in the beginning of that function that turns on the global thing, and then whenever it's done, it just turns it off. All right, so, okay. Basically the takeaway is that it's all about this trick, the side table trick. If you just organize it this way, you put the right stuff in it, you can do implicit interpretation, and I prove that it's fast. So it's, on par with a production interpreter that does rewriting. It's not on par with every rewriting interpreter. There are at least 2 examples that are faster, but it's lower memory overhead. So you only spend about 30% of the original code with this side table. Interpreters are this super weird beast where the implementation language really matters. Not to crap on Virgil, which is my own language, but boxing everything was not a great idea. I did not get the signal that I wanted. It was mostly about that value boxing. There's other overheads in there too, bounce checks and stuff like that. Virgil is never going to get the same code that I got out of handwritten assembly code. Maybe C would get close, but the implementation language ultimately, this is all the black magic is still there. The other thing is I wrote the Virgil interpreter, the one that's nice that uses ADTs and all that. It's got a lot of first class functions, and it's got it's supposed to be readable and editable because it's a research VM, right? In order for all that to go away and to even get closer to what the assembly language one that I wrote looks like, a lot of inlining and other optimizations would have to happen. So all that really matters for interpreters. Interpreters are super sensitive to this kind of stuff. And of course all the bounds checks, everything that I did. So getting to JSC's interpreter performance, I used every trick that I could think of. There's a few that are left that maybe I can challenge people to see if they can beat me, but this is not something that you're going to necessarily get out of just your random compiler. So I think this is one of the places where handwritten ASM still have classes of compilers. Although I would actually welcome somebody trying to do the same thing and see if they could get the same performance. The other thing is like all those tricks, like it was like kind of 50%. I don't know who wants to really spend 50% of it, or spend all their time doing that for just 50%, but that 50% got me over the line for getting in the same category of performance. There's always minor tuning to do, for example, like tinkered with like maybe if I just rearrange the code in memory, it'll help a little bit. That helps like 5%, you know, it's like you find stuff like that. I'm done, I'm not doing that. So if somebody wants to pick that up and publish another paper that says, look, we got another 20%, go ahead. So I've been working on things in Wizard which are trying to advance WebAssembly as a standard, right? Experiment with garbage collection and things like that. So I implemented that in the virtual interpreter, so the ultra slow thing, but the x86 interpreter, I didn't do that yet. And I've been thinking about the tricks to make that fast. And I think there's a whole family of tricks that I need to make that fast. So I don't know if that's a whole paper there, but like you could maybe stay tuned to watch the code repository, watch those fly by. SIMD is, so I actually prepared for SIMD. I have the value representation for SIMD. Wizard does all the verification, understands the type system, and passes all those tests. I just didn't implement those instructions because it's like 250 something instructions, and they're like all of them are just basically mapping to a single x86 instruction, which I didn't yet add to my assembler. So it's just a lot of work. Exception handling is coming too. I think what that boils down to is that the side table actually doesn't, I'm probably not going to handle that with the side table, other than obviously you have to jump over, like if you hit a catch, you have to jump over the catch because you didn't actually have an exception. But actually handling an exception requires a search that probably the side table doesn't help with. So it's probably going to be like another side data structure that you have to search in the runtime. And then it's got this cool instrumentation API. You could theoretically write a debugger on top of that, and that's the plan. So like, I want to make Wizard to be a platform that people experiment with WebAssembly, and they, for example, implement their languages on top of WebAssembly. They're going to need to have a VM where they can see all this stuff. I think that's a good future direction to make all of this work actually useful to other people that don't want to stare at assembly language. I started working on a baseline compiler, and then integrating them with the fast interpreter. There's a really important thing about the layout of execution frames. If you pick the right execution frame layout and you use the same layout with the baseline compiler, then it's really easy to switch between baseline code and the interpreter, both directions. So I look forward to doing some of those tricks here. So that means that you can do stuff like run mostly fast, and then you hit a probe where you hit the debugger or you hit an exception or whatever, and then you go back to the interpreter just by swapping a few things in the frame. So it will use the same value stack layout and things like that. But all that needs to be integrated. I think that's my last slide. So,
all right, thanks, Ben. Appreciate it.